Good afternoon. We're going to start the online training this week with a topic on DVT OPC communications. We're going to learn how to configure a DVT OPC server to exchange information between DVT cameras and OPC clients. We'll talk a little bit about what OPC is, and then we'll discuss how our OPC server communicates with the cameras to extract information from the cameras, and with OPC clients to post that information on the network so that OPC clients can access that data. So what's OPC? OPC stands for OLE for process control, and OLE means object linking and embedding, and it's a Microsoft technology that allows for linking elements from different applications. For example, you can drop an Excel spreadsheet into an OPC client, so you could communicate between different applications, including, for example, if we take that same example of taking an Excel spreadsheet, we can drop that into Word. The transfer of information or data between the two applications is done using DCOM technology, or distributed COM technology. So that was a Microsoft established technology that was spread out throughout the industry. OPC then is used for connecting different data sources together in a common interface. And this interface, which is the backbone of communications, is this OLE for process control. OPC is supported by many industrial devices, some PLCs, controllers, SPC and HMI packages, etc. And the idea is that OPC is a common framework and a well-established format for transferring information or data periods that will bring together different applications. As long as there is an OPC compliant server, you can share that information with any OPC compliant client, either locally or over a network. And this way, OPC offers plug-and-play capabilities. An OPC client can actually discover OPC servers available on the network and establish connections really quickly and painlessly. Once that connection is established, then data transfers occur between the OPC server and the client. There are many different clients, but all of them should be able to automatically detect any OPC server available on the network. So the DVT OPC compliance server runs on a PC. It is not embedded on the camera, so you do need a PC to run the server. Of course, that PC can be on a network, and many other clients can be on that same network and access that information through the network. The OPC server connects to multiple cameras, or can connect to multiple cameras and gather data from them. And we will talk a little bit about how that information gathering is done behind the scenes a little later in the presentation. The OPC server is configured through a graphical user interface, which is the OPC configurator, and this is what we will concentrate on, because really the server, it's only a means of transmitting data or exchanging data. The configuration of that server and how the data is being transferred is done through the OPC configurator user interface. The server is not always running continuously. What will happen is the OPC configurator will create all the settings for the server, and the server will start automatically upon any OPC client connection. So if there is any client on the network that is trying to access the server will start up and make the connection. So the configuration is saved or stored as a file on the PC where the server was configured, where the server is running. You can actually take that configuration file to a different computer, and the OPC configurator will recognize it just in case you need to transfer your server from one PC to the other. Let's say you have to, you're updating or upgrading your computers on your network. Well, you can take that configuration file with you and save it into the new computer that will act as a server and where the OPC server will be running. And that way it's kind of a painless translation there. So this is a sample network configuration for OPC. You have different OPC client, and you could have different OPC server. And one of them could be an OPC server that is connected to DVT cameras. Once those cameras are linked together with our OPC server, any client on the network can access that OPC server just like any other OPC server can be accessed. So it's basically a client-server architecture over a distributed network. So again, the OPC configurator is a graphical user interface that you use to configure the server settings. The OPC server, like I mentioned, is not always actively running. It starts communicating upon an OPC client connection. And we'll see later on that the configurator tool has a monitor view. This monitor view is basically an OPC client, but an OPC client that only allows monitoring access to the OPC server. That way, you can test and troubleshoot your settings from the same OPC configurator utility. This is an overall view or an overview of the DVT OPC configurator. You set up address spaces, which really means DVT devices. You can set up multiple devices here, including an emulator. So you can connect to a DVT emulator just while you're doing your application development or application evaluation or even troubleshooting and testing. You can do that through a connection to the emulator, and that's what we'll use today. You can also do data value conversions. We'll look at this a little bit later on. But basically, this is a way to convert your values into engineering units and specify instrument ranges. And we'll look at that later on. You can configure simulation signals. This is something that is not very frequently used, but it could be useful if during your troubleshooting and setup stage of your application. You can create ramp signals, random signals, sinusoidal signals, etc. We'll look at that later on. What that will do is you can then map any of these simulation signals to any of your tags. So for example, if you're doing, let's say, encoder simulation on your emulator or even on a camera, you can simulate your encoder pulses without actually being connected to an encoder. Of course, be aware that there's going to be a delay inherent to Ethernet communications, so it's not going to you're not going to be able to achieve the same speed as a regular discrete encoder. there is also simulation signal. There is also alarm definitions that you can create so that you're verifying that your data is within a certain range, and you can create an alarm that will be picked up by your OPC client once your value, any value, falls out of your given range. And there is also some device parameters that can be set. These are individual to each address space or to each DVT device. And this is an example where we're using the multiple register device parameter settings to really interpret data. It controls what type of data transfers you're doing, if you're doing multiple registers versus a single register, ranges of registers that you're trying to read, and it also controls a little bit how that data gets interpreted in terms of, for example, being able to swap words within your data value, and that will come in handy in some cases when we're communicating floating point values and even integer values. So any 32-bit value, you will have to do this, and we'll look at that later. So configure a device. When you first start up, you need to configure your connection to a specific device. So what does that mean? You're going to specify the IP address. There is no browsing capabilities at this point, so you do have to know beforehand what your camera's IP address is. There are other values here that you generally don't have to change, like the TCP port. That's pretty standard. That's 502, and the reason for that is that our OPC server uses Modbus to communicate with the camera to extract certain types of information. The OPC server also uses native commands or system terminal commands to communicate with the camera. So that's how the OPC server gets its data from the DVT device. It uses both Modbus connections and system terminal or native command type connections.
Eduardo?
Yes.
This is Greg. So we're only using the Modbus registers in the Intellect?
You will see later on that you actually have access to reserved registers for both Intellect and Framework. We know that the mapping of the individual I/O bits or the virtual I/O mapping is different for Framework in Intellect, but the OPC server supports both, and that's done automatically. You don't need to configure anything. But when you do need to create or any multi-general data transfer, multi-purpose data transfer, then you will need to configure those tags or write to those registers on the Modbus address space on the camera.
Okay, thank you.
Okay. All right, so let's go, actually, before we move on, go and share the OPC configurator. I'll show you what I mean here. Okay, so in the OPC configurator, again, first thing you do is you generate or create an address space or a DVT device, and this is what I've done here. I've created a connection to an emulator, and this is what I meant before. Because the OPC configurator doesn't detect automatically whether you're connecting to a system that is running Framework or Intellect, and those two systems have those two software and firmware options have different virtual I/O mapping, and we provide the I/O mapping automatically. we do then this for both systems, Framework and Intellect, for each device.
Right, and that way we don't have to convert the registers from the DVT registers to the Modbus?
You will have to do that if you're creating general purpose data transfer. So let's say you want to measure something and you want to transfer the result of that measurement on your application, then you would need to create an automatic data transfer, and that is received from the Modbus register space. In
Right.
Framework, the Modbus registers and the general purpose DVT registers share the same space in memory. So because of that, and because the DVT OPC configurator is in terms of Modbus registers, you will have to make that conversion only for Framework and only for general purpose data transfers.
All right, thank you.
In Intellect, you don't have to do that because it is clear on the Intellect side that you are writing to Intellect or to Modbus registers. And the OPC configurator knows where those are, and you can give the Modbus address straight as you see it in Intellect. But the Modbus address for Framework connections will be different than that register to which you're writing your data. And we'll do an example of this using Intellect.
Okay.
So besides the virtual I/O, which you have access to each individual one, by the way, I have here open the monitoring view, so we're getting a little bit ahead of ourselves. But we'll talk about that in a minute. Besides the virtual I/O mapping, you also have other type of inspection parameters already pre-mapped, such as the internal product ID. This is the ID of the product that is currently set up as the inspection product, and you can get access to that value. This is not a digital ID; it is the internal product ID. You also have access to some inspection statistics value. You have conflict counts, you have inspection counts, acquisition times, etc. So this is kind of general purpose inspection statistics data that you have access to.
Eduardo?
Yes.
Later on, when you go into the Intellect interface, could you show what's the easiest way to get that internal product ID?
In Intellect, the internal product ID is not necessarily always displayed. You would have to actually do a product query to find that out. What's displayed on the user interface, and more specifically on the product management user interface or part of the System Explorer, is actually the digital ID, the ID that is assigned to a product for product selection.
I see. So we can't get that internal product ID from the product manager? It's not there?
It's not there. No.
Okay, thanks.
And that internal product ID is used for some advanced applications where you're using native mode commands or system terminal commands, because many of the system terminal commands that are product specific or for some product specific function use the internal product ID rather than the digital ID. But this is not something that you would generally need.
Thanks.
Right. So this is pretty much what's pre-mapped and what's available right from the start. But most of the times, besides the I/O, which is very helpful, for example, you can trigger a camera through OPC. You can relearn different models for different tools or colors for color tools, etc. Anything that can be relearned through a digital relearn signal, you can do it as well here, because again, you have access to the entire virtual I/O map. So this is very, very useful indeed. But generally, you also want something more. You generally want some output from your application, be it a specific classification application where you're looking for what type of model is presented to the camera, what type of part is presented to a camera, or if you have a measurement or gauging application, you want to know that, what you want to get at those measurement values, or any other type of application you can think of. You generally need some data besides the discrete fail and pass type signal, which you do have access to through the outputs. There's the general fail and passing signal. So generally, there is a need to add specific values. And the way this is done is you right-click on your device, and under the new option here for the context menu, you can create either a new folder or a new data item. Depending on how you want to organize your data, you may want to create a folder, and I don't know, call it custom data. Apply. I'm going to turn off monitoring view here. There are some. The reason why I want to turn monitoring view here is because there are certain settings that only take effect after the OPC server has been restarted, and the OPC server shuts down basically, or stops communications when there's no OPC client going on, and the monitoring view is one of those OPC clients. So I'm going to turn that off. And I would want to, so sometimes you'll notice that some changes that you make on your configuration, if you're while you're displaying your monitor view, sometimes those changes are not apparent immediately. It takes a while for those changes to take effect, or maybe they just take effect after you restart your monitor view or any other client that is connected to the OPC, to the DVT OPC server. So I generally have any clients disconnected, or all clients disconnected, make my changes, and then bring up the monitor view to kind of test and troubleshoot and make sure everything's working, then shut that down, and then open any other OPC client I want to make a connection to. So for each folder, you can then add subfolders, or you can add a data item. We're going to stop here because, and now we're going to move to Intellect, and let me show you an application that we're working on, and then let's see what type of data we would want to transfer. Stop this, and we're going to bring up Intellect. All right. Okay, so in this case, I have an application where I am using two edge tools to find the location and orientation of this part, and then I'm doing some measurements here. First of all, I am measuring the radius of this large through hole. I am also measuring or verifying that there's 3 holes here, so I'm counting the holes or these features, and then I am finding center points of these through holes and finding the angle between the lines connecting the centers of those circles or holes. So I've created position reference here where my top edge is. Here's the order. You can see the order of execution on this column. Top edge is my main reference, and then I have left edge and all the other measurement tools. I'm just going to go through all these and verify that they all get their position reference and they're fixtured correctly. Okay, so now I want to, let's say I want to transfer some data here. We can transfer the number of, a verification of the number of features here. So I want to know how many features are being counted here by this tool, and that always has to be 3. I also want to maybe send out the diameter of this hole, and I want to maybe send the angle between these 2 lines. And I want to communicate this through the OPC server to any other OPC client. The way I would do that is I need to expose that data through to the OPC server. We want to do that using Modbus. So first thing I want to do is under System, go to Modbus TCP. I don't really need to. Here the OPC configurator is the master, so I don't need to configure anything under the Modbus master's interface. I just need to create to provide those values through Modbus to the OPC server. I can do that through scripting functions or by just creating tags on the Modbus register space. So I'm going to create a tag here. Automatically it starts on register 16 because 0 through 15 are mapped to the virtual I/O, which is already available through the OPC server. So I will say here our feature number. And because this is going to be a small number, usually 3, that's what we want, I'm going to leave that as a short. And this is something that we need to make sure that we are aware of, and that is the different data types and their size or the number of bytes they occupy. Because the terminology is a little bit different between Intellect and the data types for that tag and the OPC configurator tool and the data types for each item that we add there. So let's keep that in mind for now. Leave it as short, and under source expression I'm going to write here number, or the count, number of features that the feature count tool is detecting. This tag is updated at the end of the inspection, so I have to trigger the camera to see that change. Right. I'm also going to add. Notice that this is a short data type, so it occupies 2 bytes, which is 1 Modbus register. And I'm going to add radius of the large hole, and I'm going to convert that to a float. Float is the only floating point on data type that is supported by OPC, by the OPC server. You cannot write 8 bytes or data types. In this case, will be double. We cannot write doubles, so we will write floats. And we're going to map that output to that tag. I'm going to take an inspection just to update that value. And I'm going to add also the angle value. I'm going to convert that to a float as well. I want that to be a floating point number. Notice that the start address now for the next tag is 19 because of the floating point value occupied 4 bytes, which is 2 Modbus registers. So I'm going to find the angle for that tool. Make sure that it's there. Yep. Okay, So these are the values I want to, and let me save that product setup. These are the values that we want to transfer. Back to the OPC configurator. Remember that we mapped these values to registers 16, 17, and 19 respectively. And that number of features is actually a short, which is a 2-byte integer. And the other two values are of type float, which is a 4-byte floating point number. All right. We're going to go back to the OPC configurator. And under the custom data folder, I'm going to add a new data item, or a few new data items. One of them is the number of features. Notice that this is not automatically discovered. The types of tags that we are exposing are not automatically discovered by the OPC configurator. You do need to add them manually there. So, say feature count. And this is where knowledge of the information and the settings on the Intellect side comes into play, because now we have to specify where's this data and what type of data it is. This is a holding register. Really, and this is Modbus lingo now, but our Modbus register space is it's a single unique register space. So the different Modbus types are not separated out. Generally, you want holding registers here. This is something that you generally don't need to change. The type of data does need to change, and you have to choose the type depending according to what you configure in Intellect. And this is where you have to kind of do a mapping between the Intellect data types and the OPC server data type. Short, we said it was a 2-byte int. So that's called int in this case. We can see that it is a 2-byte value here. We have to specify the starting Modbus address. Remember, that was 16 in our case, and that's pretty much it. If you had an array of values, and they have to be the same data types. Let's say you have an array of feature counters. Let's say that you had several feature count tools in different places for your application. You could create a vector or an array of them, and you specify the number of elements. So this is not the number of bytes. This is the number of elements, in this case ints, that are basically back-to-back in memory. But this is not necessary in this case. So we'll just create that, apply, and we will add the other data items. This is radius. Radius was written into register 17, and it is a float, so that's a real value.
No. I was going to say the D is not a double, is it?
No, D stands for, it says double integer, but it's actually just double refers to the size, so it's a 4-byte.
Right, I see that.
But it's actually, there's only one floating point data type, and that's real.
Okay.
Okay, and then I'm going to add angle here. The angle, it's also real and starts on register 19. Okay. Now going back to device parameters, notice that we have selected here, instead of the default device parameters, we have selected custom, and we have selected multiple registers. So let's explain a little bit what these device parameters do. So if you go to the device parameters section, there is two predefined settings. One is one at a time, which means we're only going to transfer one register. And you specify which value you want to read or write. You can also specify multiple registers. This is also predefined, and this specifies the maximum number of data that can be transferred for a particular data type: coils, inputs, holding registers, etc. You can change that.
Eduardo, would that be similar to a block transfer then?
Yes, these are block transfers. Again, in our case, it's not as important to distinguish between them, except if you're maybe writing a bit field data type. In other words, some sort of integer where each bit represents a different value. You can do that as well by using coils. But in general, you're going to transfer some either integer or floating point value or string. In that case, you will always use holding registers. The important part here on multiple registers is a word swap, and we will see why that is. We can show you that on the monitor once we get to the monitor view. But the way it's important is because by default, the OPC configurator interprets data a little bit different than the way that Intellect sends out these pieces of data through Modbus. And we need to do a word swap so that the data is interpreted correctly, and we have the correct value. So I'm going to make sure that is set up here. And this needs to be used every time you're using any data type that is longer than 2 bytes. So if you're using a DINT, which was a 4-byte data type, or if you're using a real or a UDINT, anything that is over 2 bytes, you need to use that multiple register value with the word swap checkbox checked. Okay, I think we're ready to go to the monitor view. That's F12. And what you're going to view here is anything. You have to click on the folder, and then you will see any value that belong to that folder. So we're seeing here all 3 values. There are checkboxes here because you may not want to inspect every single one. Remember, this is mainly for troubleshooting. In this case, I am going to check all of these. These are the values that start to come through. This angle left it at int. There we go. It took a while to set up, but now we're seeing all the values that we see on Intellect. And as we trigger different inspections, we will see these values change. One thing I wanted to mention again is that monitor view, it's only for monitoring purposes. Any OPC client will be able, of course, to both read and write to these values. So there could be a value that is set as reading or writing to the camera instead of reading from the camera. And you can set these values from your OPC client. All right, let's I'm going to talk a little bit about other features. We already saw the monitoring view. This is a monitoring view of the reserved outputs, where I was looking at the inspection toggle here and seeing that change. There are other features not very frequently used. For example, you could do conversions. And if you select the type of conversion you select no, it's basically the only thing that this does is that it converts your data value into a floating point value. This is very rarely used because you could make that transfer, that setting from the very beginning. So you could, from the very beginning, set up that data type as a floating point value. For linear and square root, basically that defines the relationship between the engineering units and the instrument ranges. But this is a way to convert the values that you're seeing to some sort of instrument range, so that you actually look at that instrument range. And that conversion could be a linear conversion or a square root conversion. You could also create any other different conversion that you want. There's 3 different conversions done automatically. There's one that basically converts your value on a value from 0 to 100 or a value from 0 to 1,000. So, for example, if you're reading an intensity value that goes from 0 to 255, and you want to bring that to 0 to 100, you can do that. You can specify your ranges, your instrumentation ranges. Again, something that is not necessarily always used. Sometimes it might be used for statistical process controls type of packages, and there are many of those that support OPC. We already looked at device parameters, but basically it's a way to configure different data transfer settings depending on the Modbus data type, and a way to interpret the data types by selecting to swap all the bits. So basically we'll go from big endian to little endian, or swap words, which we did for our for both our floating point values. You can also do alarm definitions, and this is an example where you're going to update. The update rate refers to how frequently this value is actually looked at for alarming, and you can hook up this alarm. You can pick this up from your OPC client and hook it up through your HMI package to anything you want, maybe an on-screen warning, or maybe you pass that along to using your HMI package to your PLC, which might turn on siren or something like that. But it's a way to qualify your levels and create different alarm definitions. And you can specify whether to return to normal or not, or just stay or keep the alarm on. If you return to normal, it'll return once the value has come back to the appropriate value within your range. You can specify also a severity of the alarm, so that this high and low basically have a 500 severity, but if it goes very low, in this particular case below 100, if your value goes to 100, then your severity increases. And many HMI packages will have also different levels of alarms that can be mapped to these severity values. All right, so what types of products support OPC? I mean, there's many different products that support OPC from any of these manufacturers and many others. Generally, OPC is used in conjunction with PC applications. These could be custom PC applications, or these could be HMI packages, SPC software packages as well, etc. It's just a different, just another way of sharing data between products. It could be between our camera and an HMI package and a PLC, etc. Anybody has a specific question?
Wondering if you had planned to go over this, how to get it, what you showed right there was how to get it from the Intellect over to the configurator or the server. Is that accurate?
Yes.
What would we do if we wanted to get it over to an Excel spreadsheet, for example?
So an Excel spreadsheet could be an OPC client, and in this case, each OPC client has different ways of configuring connections to OPC servers. To that effect, I'm going to show you this particular case.
Or it doesn't have to be Excel. I mean, just anything. If you could just give us an example of what's a good way to think about this at this point.
Right. Generally, this is a free version of an OPC client. And let me show you this sharing frame. Do you see everything that's inside this frame now? You should see
most of
the
it.
configurator, client, and Intellect at this point. All right. So I have here an OPC client, and as you can see, the OPC client will generally browse for any device or any OPC server that's available, and these are posted by each server. You can see some other OPC servers here, Cognex Insight server. The DVT OPC server will show up as OPC server DA, and this refers to OPC DA, which is one of the technologies used by OPC, or one of the variations of OPC. So as you can see, the OPC client automatically detects anything that the OPC server is exposing. So we can look here at all the devices that have been configured, and then within the emulator, which is what we're looking at, we see these values here. We see these values that are being read directly from the OPC server, which is already running. I could also write some of these values. For example, let's look at trigger. I'm going to try to trigger here. I'm going to trigger from Intellect, and you'll see values changing here. We went to the next value. And you should see the tag browser here changing values. As Intellect updates its tags. So you should see that those values being changed here. There are many different. What's that?
I was going to say, is Intellect updates those values? Those are updating in the client as well?
That's right. As Intellect updates these values. In this particular case, the values, because they're product tags, they're updated at the end of an inspection.
Continuous inspections, right?
What's that?
Right now you're running continuous inspections?
No, I'm just triggering manually here from Intellect.
Oh, gotcha.
In trigger button.
Okay.
You can set it up as continuous inspection as well. There we go. You should see those values changes. Different OPC clients have different ways of connecting these values, but in general, once you have an OPC client that is OPC compliant and can detect any OPC compliant server, it should be a matter of just browsing through the data that you have exposed through the server. You'd see those changes.
Great, thank you.
All right. Any other questions? So there are a couple of key points when you're configuring an OPC an OPC server for connecting to DVT devices. First of all, you need to remember that if you want to transfer general purpose data, you need to add those values to the Modbus address space. So I've created Modbus tags here. You also have to make sure that if you're transferring anything other than a 2-byte value, you have to specify any device parameter really that swaps words so that the OPC clients can interpret correctly those numbers. Otherwise, you'll get numbers that don't make a lot of sense. And the other couple of points is that when you configure a custom data item on the OPC configurator, those are not automatically detected. So the DVT OPC configurator doesn't automatically detect Modbus tags that have been set up through Intellect or Framework. You have to manually add them. You have to specify the starting Modbus address and the data type. Once you remember those key issues, everything should be pretty straightforward. Remember, you can use the monitoring view only for monitoring purposes, just to make sure that everything is okay. There's a timestamp on those values, and there's a kind of a quality depending on this quality refers to several things. For example, the tag was always acquired. There were no problems. There were no packets that got skipped or polling periods where we couldn't get this data. If we delete, for example, one of these values, one of these tags, the value will still be there. It wouldn't change at all because the registers are still there. But if there is some sort of Ethernet problems, then you would see those that quality drop, obviously, because we start dropping those values, and the OPC server can't get to those values. But in general, this is a good, no good type, not good type situation. And there's a couple of extra features that you can use to create alarm definitions and simulation signals and any engineering unit type conversion. All right, any questions? All right. I think if there's no questions, we can stop here. Remember that at any points, if you have any problems, you can contact us here at Cognex Tech Support, and we can help you we'll try to help you with any application problems you have, and also invite you to our next online training next week at the same time through the same live meeting console. So if there are no more questions, I thank you and wish you a good afternoon.
Thank you, Eduardo.
All right. Thanks.
Bye.
Bye-bye.